So far we were talking about systems that are smooth everywhere. Smooth means everywhere differentiable. That means we have been considering equations of the form x dot is equal to f of x, where x is a vector and this function f is continuously differentiable everywhere. We are considering that kind of systems. Now, in nature as well as in engineering, there exists a large number of systems where there is some kind of a switchover action. For example, you might imagine that the state space is divided into some kind of a compartment, so that if the initial condition is here, it will be guided by some equations of the form x dot is equal to f1 of x. And while doing that, if it somehow intersects this, then the system equations that govern the evolution of this curve is the solution of the differential equation, the state space trajectory, that equation it will change to something else. For example, so that it will then go in some other direction, doing some other thing, and then again when it comes back, again it undergoes a switching and it goes in some other direction. So, you might imagine situations like that where there is some kind of a switching. Such systems are called switching dynamical systems, also called hybrid dynamical systems. The word hybrid comes in the context of where the continuous time evolution, there is also interplay between some discrete events, in this case discrete switching events. Now, what happens in such cases? Now, when we try to understand what happens in such cases, try to picture that such systems will also have to be discretized. That means, you need to obtain some kind of a discrete time description of the system, and we know that discrete time description of the system is obtained by the Poincare section, the method of Poincare section. So, if there is a system like this, the normal description would be something like this. System description would be x dot is equal to, it will be f1 of x if x is in the compartment say R1, f2x another function if the state x is in the compartment R2, and so on and so forth. So, this is the general system description that we are talking about. But first, in order to understand what happens in such systems, let us consider only two such compartments in the state space. You might imagine what is the practical implication of this. For example, there are a large number of switching circuits, power electronic circuits are switching circuits, where there is an on state of the switch and there is an off state of the switch. During the on state, it follows one set of differential equations. If it is in the off state of the switch, it follows another set of differential equations, and obviously this is the description that we need. But there are also many other practical examples when this happens. For example, imagine the bouncing ball. Imagine the systems, mechanical systems where there is some kind of impact. So, when there is an impact, it goes a bit to the other side depending on the flexibility of the impacting surface. Then, so long as it is not impacted, it is governed by one set of differential equations, and if it is impacted, it is governed by another set of differential equations. Schematically drawing, we would draw it like this. There is one spring and there is one damper connected to a mass, and there is some kind of a force acting, which makes it oscillate back and forth, and there is a wall. So, it could hit the wall and come back. If the wall is rigid, then that will result in instantaneous reversal of the velocity, while if this surface is somewhat soft, then it will go into that, and while it goes into that surface, obviously the system equations change. So, this exactly brings in this kind of description. You might also imagine the situations of hydraulic systems where there is some kind of a closing and opening of valves. So, when the valve is open, it will be one set of differential equations. If the valve is closed, it will be another set of differential equations. And a good example is the human heart, in which there are of course valve openings and closings. There are triggering events caused by the heart action is started by a triggering action. So, that is also a non-smooth behavior. So, the smoothness, notice smoothness relates to the differentiability. Now, here when it goes from within this compartment, at every point it is differentiable, this curve is differentiable, right. But the moment it hits and goes in another direction, at this point it is not differentiable. So, at this surface, the switching surface, the behavior is called non-smooth. This word non-smooth should be understood. It means that it is not differentiable on a specific surface or a switching plane. If the original system is n dimensional, the switching plane can be imagined to be a n minus 1 dimensional hypersurface. So, that whenever the state comes and makes a contact with that hypersurface, it goes into another set of differential equations. So, how do we analyze such systems? The moment we try to do that, try to picture this kind of an orbit. Suppose it is a 3-dimensional system, and suppose here there is a switching surface. I am drawing some kind of a switching surface, it could be anything else, but I am just drawing. Now, suppose there is a orbit something like this. Fine. Now, this orbit does not intersect the switching surface, it always remains in one side of the switching surface, and therefore, all points of the orbit would be smooth. But you might also imagine a situation where the orbit is something like this, but it intersects, goes in the other side, comes back and then goes. Now, what is the difference between these two? Obviously, the difference is that it has intersected the switching surface, gone to the other side and come back, and that is how it completes. Now, in both cases, you might place a Poincare section. For example, if you say place a Poincare section here, then you will see the mapping as this point mapping to this point, and you would get some kind of a functional form of this mapping. Now, you might not be able to obtain the functional form in in closed form, but nevertheless you know that there is some function that maps from this point to that point. Now, if you do the same exercise in this system, you would place the Poincare section here, and you would now talk about the map from this point to this point. Now, obviously, just try to understand logically, if you think that there is some kind of a expression for the map, will the two expressions be the same? Obviously not, because in going from here to here, what happened? It went through this and it landed up here, right? While in going from here to here, here to there, it is like this. It goes like this and it comes here. So, all through it goes through one set of differential equations, while in this case, in going from here to here, you have to go this way. It comes here, goes across the switching surface, and there is another set of differential equations that describes its evolution, and finally it comes here again, finally. So, obviously, in order to find out the map from this point to this point, you would need a much complicated things to be performed, and obviously the functional form will be different. Now, these two different functional forms will have a critical value where you might imagine, let me draw in another piece of paper. You might imagine that starting from a point and then it just grazes and goes. It does not go to the other side, it just touches, but does not really go to the other side. This orbit will be a critical behavior between these two types of behaviors, and if you place the Poincare section now, it is not difficult to realize that starting from this point, it maps to this point, means it goes like this and comes back here. Okay. If you started slightly this way, then it would have not grazed. If you started slightly that way, it would go to the other side and come back. So, this point is sort of a critical behavior between these two different types of behavior, and it is not difficult to see that such points, there can be many such points. That means, there can be another point here which will also have the property that from starting from here it will graze and come back here. Starting from another point, it will graze and come back here. Therefore, there will be a line that will divide these two types of behavior. In this part, it will go to the other side, that means it will undergo the switching. Starting from this side, it will not undergo the switching. And the functional form in this part will be one type like this, and the functional form in this part will be another type like this. What does it all mean? It means that at the end of the day, you have a discrete time state space. If I now blow up this in the next page, it will be some kind of a description like this, where in this compartment it will be x n plus 1 is equal to some function x n, and in this compartment it is x n plus 1 another function of x n, where x are vectors. All right. So, what is so holy about it? What is so holy about it is that we know that in such a system, as you change a parameter, the location of the fixed point will change, the local linearization will also change, the eigenvalues will also change, so on and so forth. And we know that when the eigenvalues exit the unit circle, cross the unit circle, you have bifurcations. So, it might happen that the fixed point is here, and as you are changing the parameter, you are always keeping track of the local linearization and keeping track of the eigenvalues, and as you change the parameter, the position of the fixed point moves and it crosses the unit circle. The eigenvalues, one of the eigenvalues crosses the unit circle. When that happens, obviously we can explain what happens in terms of what we have already learned. Why? Because we have already learned that in the, if this is the unit circle, and if the eigenvalues, one eigenvalue goes this way, then what is it? It is the period doubling bifurcation. If this is the unit circle, circle of radius 1, and an eigenvalue goes and hits this way, what is it? It is a saddle node bifurcation. If you have a unit circle like this and eigenvalues move like that, what is it? It is a Hopf bifurcation or Nymark-Sacker bifurcation, giving rise to the birth of a quasi-periodic behavior. These are all known. So, if similar things happen while the fixed point is in one compartment, we know what happens. But there is also the possibility that with the change of the parameter, a fixed point may come and hit the border, and maybe it goes to the other side. If it goes to the other side, then obviously so long as it is here, its evolution is defined by this. So long as it is here, its evolution is defined by this one. They will have different Jacobians, they will have different eigenvalues. In other words, what will happen is that the moment it hits, the eigenvalues will discretely jump from one place to another. It may be so that the eigenvalues were, so long as it was here in this side, suppose the eigenvalues were say here and here. What is it? An attractor, a flip attractor, because one eigenvalue is negative. But when it landed here, when it crossed the border, it is possible that they discretely jump to this location, which means now it has become unstable, it has become complex conjugate. So, it will lead to a spiral outward orbit and so on and so forth. So, you see there is a possibility of a sudden, discrete and abrupt change in the behavior caused by this kind of phenomenon. That kind of phenomenon, that class of phenomenon that are caused by the collision of a fixed point with such a border line is called border collision bifurcation. All right. Fine. So, let me give an example now. Well, this is a 2D description. That means, here we are considering, since I have drawn it in 2 dimensions, it means that x is a 2-dimensional vector, x and y. So, here you would say x, here you would say y, and so on and so forth. But there may also be situations where it is just 1-dimensional. In that case, what does this picture look like? In 1 dimension, you can draw the graph of the map. So, in that case, you might end up in a situation something like this. Say, in one side, say this is the borderline, it is x n and this is x n plus 1. And suppose this is the border. That means, for these values, of x n, it will have one functional form. For those values of x n, it will have another functional form, and it is divided like this. So, suppose so long as x n is less than this value, the behavior is something like this, smooth, but at this point there has to be a non-smoothness, the character has to change. So, it might be like so, all right. So, it is not difficult to see then that in 1D also such things can happen, and let us start to work on this kind of idea, because 1D, one dimension is easier to understand because you can draw a graph. But first let me give an example, very simple example, an example that probably I have already done, but nevertheless for this context let us repeat. Let us consider the power electronic boost converter, where you have got a battery, you have got an inductor here, and you have got a switch here. Here is a diode, here is a capacitor, and here is the load resistance. This is the load. Now, this explanation you should recall what happens when the switch is on and off. When the switch is on, then the current through this loop builds up, because it is the voltage connected across the inductor. So, the current builds up linearly, and when the switch is off, then the whole circuit is connected, the diode is forward biased. So, the current will flow like this, and the energy that has been stored in the inductor will then be going to this RC network. So, the energy shifts from here to here, the energy in the inductor then drops, the inductor current as a result falls, and if the inductor current falls, then the LDI dt will have a different sense. So, if this is positive, this is negative, this will become positive and this is negative. As a result, this voltage and that voltage will add up, which appears across the load. So, the load sees a voltage that is bigger than the input voltage. That is the concept of the boost converter. Now, often the control of the switch is done by what is known as the current mode control. I am not showing the circuit, but let me just illustrate the principle in terms of a diagram. Here, suppose I am drawing the current waveform, and this is the 0 level, and there is some kind of a reference value. So, this is the I reference. There is also periodic clocks. So, I am drawing the clocks. So, you might say that, okay, let me draw the clock instance all through, so that it is clear. Now, at a clock instant, the switch is turned on. So, the inductor current goes up, and when it hits the I reference, when it becomes equal, the switch is turned off, which means it goes like this. Again it turns on, again it turns off, again it turns on, again it turns off. Let me draw some more. Again it goes, but now imagine that it does not reach the I reference before the next clock comes. In that case, it goes on, okay, and then it turns off, so on and so forth. So, that is the kind of switching logic that is followed, and this red line would be the current through the inductor. Now, suppose I want to obtain the discrete time description of such a system. How will you do it? Obviously, in order to do that, we will have to sample it, because this is a non-autonomous system. There is some kind of a external clock, and we have learned that whenever there is a external periodic input, it is a non-autonomous system, and then the discretization has to be done by placing a Poincare section in synchronism with the external periodic input. So, that is what we do. We observe from this point to this point to this point to this point to this point and so on and so forth. Now, it is not difficult to see that if the capacitor is large, then the voltage here would be held almost constant. If we assume that, that means if we proceed under the assumption that the capacitor is large and therefore, this voltage V output and this is the V input is V out is more or less constant, then this will be really a straight line, because it is only this part, and the straight line will have a slope how much? V in by L. So, here the slope is M1, where M1 is equal to V in by L, and here it is when it drops, it is V out minus V in by L. So, here is the slope is M2, where M2 is equal to in that case, if you try to obtain the discrete time description, just recall we have done that already. How will we proceed? We will first have to obtain this time. So, is that visible? Yes. So, what we will do is we will say I L, this is the nth time instant. So, I will say I n, and I am trying to find out I n plus 1, is I n, plus M1 T on is equal to I ref, right, it has reached I ref, which gives me T on So, how much is the off time? That is the total clock period T minus T on. So, T off is equal to T minus I ref minus I n by M1. Then what is the final value? I ref minus M2 times T off. So, I n plus 1 is equal to I ref minus M2 T off, which is T minus I ref minus I n by M1. Okay. But this is only half of the story, because there is also a possibility of evolution like this, which means that it does not reach the I reference before the next clock. Now, if that is happening, then this one, in that case, if I take this as my I n and this as my I n plus 1, then what will be the I n plus 1 in that case? In that case, I n plus 1 can be straightforward written as I n plus M1 capital T. So, you can see that there are two possibilities, one where the map will be given by this, two where the map will be given by this, and the critical distinguishing behavior would be one where starting from a point here, it reaches exactly at the next clock. So, the I will say I border is, can you say what will be this value? It is essentially that value with which I will add M1 capital T, I will reach I reference. So, this is I ref minus M1 T. Okay. Fine. So, here you have the final description of the system. These are the two compartments and this is the borderline condition. So, let us draw this graph I n versus I n plus 1. Somewhere there would be the borderline case, say the borderline case is here. So, this is I border. below that value, below I border, that means if the initial condition is below that, obviously it reaches by like this. So, you have to take this equation in plus m1t. What will be the graph like? The graph will be the slope of the graph will be 1 and plus m1t. So, it will go something like this. Here the slope is 1. And it will reach I reference. Okay. So, this is the borderline situation where it reaches. So, if you put I border here, in this case you see that m1t cancels off, you get I reference. So, finally you get I reference. After that we have to take this equation. This equation is, you can see that this is a constant, this will be a constant, these all parts are constant, only this one is a variable part where the slope is m2 by m1 times minus m2 by m1. So, here the slope is minus m2 by m1 times in. So, it will be something like this where the slope minus m2 by m1. Good. So, this is the graph of the map for this practical system. See the similarity that we had said that a normal piecewise smooth map would be something like this, only in this case after the simplifying assumption that the output voltage is kept constant, we see that both the sides are linear, but nevertheless it is satisfies the definition of piecewise smooth. So, we need some kind of a theory for the bifurcation that will happen when the fixed point will hit the border, that means when the border collision will take place. Let us see, when will the border collision take place in this case? Fixed point, where is the fixed point? Simple, draw the 45-degree line. So, here is the fixed point. Now, with the change of the graph of the map with the change of the parameter, if it so happens that at some point it changes at go and becomes like this. Yes. Then as you change the parameter, you can see that there is a border collision occurring. So, we will try to understand the character of that. Now, it is not difficult to see that the event that will occur exactly at that point is no way related to this character of the graphs in these parts. It is only related to the slopes here. That means the local linearization in this chunk and the local linearization in this chunk. Okay. In fact, that is what is normally used. It is to our luck that it is already linearized, but in most different situations it might not be linearized. So, in order to understand what really happens, I do not need to consider the whole graph of the map, I only need to consider the linearized chunks. So, and if you make some coordinate transformation, this can be expressed as this linearized, piecewise linearized map can be expressed as x n plus 1 is equal to a x n plus mu for x n less than 0 and b x n plus mu for x n greater than 0. That is why this form is called the normal form, because just by using this you can exactly understand the character of the border collision bifurcation, which orbit remains, which orbit exists, which orbit would be stable, all that can be understood just by considering this simple map. So, let us from now onwards consider this simple map. Can you see? Yes. Okay. What will be the graph of this map? Obviously, that will depend on A and B, but it is not difficult to see that it will be the graph of the map. Okay, what is the result of variation of mu? Mu is the parameter, is that the whole graph of the map goes up and down. So, you might say depending on the value of A and B, the graph of the map is like this here and like that here. As you change mu, it goes here and here. So, this point represents the critical value of mu, at which, if you draw the 45-degree line, it will be clearer, at which the border collision takes place. Just look at the result of the variation of mu. Initially, when the mu was negative, the fixed point was here. As mu was increased, this graph goes up. It is not difficult to see that the intersection with the 45-degree line will go closer and closer to the y axis, and at this point, when mu is equal to 0, then this is the line of, this is the border line, the fixed point collides with the border line. So, border collision occurs at mu is equal to 0, and after that the fixed point moves here. Fine. So, depending on the value of A and B, we can then identify the different bifurcations that will take place. For example, in this case, what will happen? In this case, while mu was negative, the fixed point was given by the slope A. The fixed point was given by the slope A, and when mu was positive, the fixed point is given by the slope B, and in this case, the way I have drawn, both A is between A is positive, so between 0 and 1, and B is negative. So, in this case we have drawn it as B is greater than -1, but less than 0. That is how we have drawn it. And in that case, in the bifurcation diagram, what we will see, it is a stable fixed point, and in the other side also it is a stable fixed point. So, if you draw the bifurcation diagram, you will see something like this, that this is the bifurcation diagram that I am drawing, not a picture like this. Here it is x n versus x n plus 1, but here I am drawing mu as a parameter which is being varied, and here the x n. You will see that there is a stable fixed point existing for negative values of x n. So, it will go like this, hit it, and then there will be a stable fixed point existing in the other side also, it will be like so, but notice that the slope will change. So, a fixed point remaining a fixed point, stable fixed point remaining a stable fixed point, but the slope undergoing a change. These kind of events are very often seen. There is a bend in the bifurcation diagram. These are often caused by border collision, but these are not dangerous, because these are situations where the fixed point remains stable. It is not difficult to see that such situations will occur where the A lies between -1 to 1 and B also lies between -1 to 1. Okay. So, we might say that we might draw a parameter space with A and B as the axis, and we would say that if the parameters are chosen within the box given by -1 to +1 and -1 to +1 in this box, then the fixed point will remain fixed point. Good. What if I choose a parameter, say here? Notice where the parameter is. A value will be greater than +1 and B value will be less than 0, that means it is negative, but greater than minus 1. So, what will be the behavior? Let us try to figure it out. A value greater than plus 1. So, B value between 0 and minus 1. Good. Now, you see at this situation there is no fixed point. As it goes up, there will be a time when the graph of the map will look like this. Only it critically fixed point critically starts to exist, but when it has crossed 0, notice what has happened. There was no fixed point here, but at this point two fixed points have come into existence, one here, another here, right. This fixed point is unstable because the slope is greater than 1. This fixed point is stable because the slope is less than 1. It is similar to a saddle node bifurcation or a tangent bifurcation. Only thing is that in this point you cannot really call it a tangent, but it has similar character. So, this is a border collision bifurcation where you have, so I have taken A greater than plus 1 and B between 0 and minus 1. So, in that situation we are likely to observe one fixed point, no fixed point first. I will give it, I will designate it with the symbol null. Two fixed points. There is a fixed point here. Let us, it is unstable, so let us call it A, small a, and this fixed point is stable. Let us call it capital B. Capital for the stable ones in this side, A, small a for an unstable one in this side. So, this is like a saddle node bifurcation. In the bifurcation diagram, what will you observe? You will observe that in this side where mu is less than 0, there is nothing, no fixed point. But at this critical juncture, two fixed points are born, one stable, another unstable. This has been called a border collision pair bifurcation because a pair is born. Fine. Now imagine that so in this part you expect a situation in this part. In this part you expect a situation where a pair of fixed points are born, out of that one is stable. So, that is what you will actually be able to see. Now, imagine that you change B to a value somewhere here. So, what is the situation? A is greater than plus 1 and B is less than minus 1. Let us see what happens then. Now, the situation is A is greater than plus 1, B is less than minus 1. When it is crossed, it will be like this. Notice now, both these points are, two fixed points are born. In this situation, there was no fixed point, there was no intersection with the 45-degree line. But the moment it has crossed mu is equal to 0, you will have two fixed points, but both unstable. Will any periodic orbit occur? No, because if any periodic orbit had to occur, then it will have some iterates falling here and some iterates falling there. For the iterates falling here, there will be local stretching because the slope is greater than 1. This neighborhood, when it maps to here, here also the slope is greater than 1. So, all the neighborhoods will always expand, and therefore, you cannot have any high periodic orbit that is stable, impossible. Can there be chaotic orbit? Well, a chaotic orbit will occur only if the orbit is bounded. Will it be bounded? Notice that any initial condition here will tend to go like this. So, it will go away from here. Any initial condition here will tend to go like this. So, it will go towards that. Therefore, there is a possibility of the orbit being bounded, because from this side it goes to the right, from this side it goes to the left. So, obviously, it has a possibility of remaining bounded. If it is bounded, the behavior will be chaotic. But over the whole range, there is also the possibility that this point, if any iterate falls here, it will in the next iterate go here and it will come here. And in the next iterate it may, if it lands up here in this side, then there is no problem. But if it lands in this side, then it goes out, right. So, there is a critical value. As you keep on changing the values of A and B, there is a critical situation where the orbit may become unstable. Notice what is the kind of instability. This is a boundary crisis. This was the extremity. That means the extremity of the attractor and the extremity of the basin boundary, they collide, and whenever that happens, you have the attractor no longer existing. That means any iterate in this zone will keep on oscillating. Finally, it will map here at some point, and then it will go to infinity. That is a unstable chaotic orbit. So, the critical difference between the stable chaotic orbit and an unstable chaotic orbit will be where this point maps to the point, maps to a point outside, it will become unstable. If it maps to a point inside, it will remain stable. I leave it up to you to find out the condition under which the chaotic orbit will remain stable. Okay. So, you will do it before coming to the next class. It is a very trivial thing, trivial trigonometry to be done. So, we were plotting it here. In this part, we find that under some condition, in this part we are considering, under some conditions the chaotic orbit will be stable, there will be a chaotic orbit, and under some conditions the chaotic orbit will become unstable, and as a result there will be no orbit that is stable. And I can tell you, you obtain the condition, the condition is something like this, it comes to be something like this. So, that in this region you have a stable chaotic orbit. In this part, there is nothing stable. Okay, let us consider the situation here. Say I have chosen a point here, which means that A is between 0 and plus 1, while B is less than minus 1. A is between 0 and plus 1, like this, and B is less than minus 1, like so. When it goes to the other side, notice that for mu less than 0, the fixed point exists. When it goes to the other side, so what is the result? That the fixed point, as this mu changes, this whole graph goes up, this point moves this way, and finally at this point, at mu is equal to 0, this one moves to the other side, there is a fixed point, but this fellow is now unstable. So, at this border collision the fixed point loses stability, it is no longer stable. Okay. But here since the slope is greater than -1, even though it did not go exactly through the -1 point, it jumped across the -1 value, but nevertheless you might imagine that this is something similar to the period doubling bifurcation. But the period 2 orbit, whether it will be stable or not, that depends on what? Depends on, if it is a period 2 orbit, there will be one iterate here, another iterate here. Here the slope is A, here the slope is B. So, periodic orbit, period 2 will be stable if AB is less than 1, right, or we can say mod of AB is less than 1. Now, this means that over this whole range you will not see a period doubling really. You will see a period doubling only if the mod of AB is less than 1, and that yields a range something like this. So, in this range it will be period doubling, but in this range it will not be. Period 2 orbit will be unstable. If the period 2 orbit is unstable, is it possible to have a period 3 orbit? Well, not impossible though, because there may be 2 iterates in this side and 1 iterate bringing back here, possible. But in that case, how would you obtain its condition of stability? The condition of stability will be 2 points to the left A square and 1 point to the right B. This magnitude has to be less than 1. So, this is for period 3. Not only that, you also have to find out, you also have to worry about whether the period 3 orbit exists. In order to find that, all you need to do is to imagine, if you are imagining a orbit something like this, 1, 2, I am not going to draw, but nevertheless 2 points to the left, 1 point to the right. So, you will have to write down the equations as x n plus 1 is equal to A x n plus mu, x n plus 2 is equal to again A x n plus mu, x n plus 3 equal to, now it is on the right side, B over this plus mu, and this has to be same as x n, then only the period 3 condition is satisfied. So, solve this and obtain the condition for x n, that will be the condition of existence of period 3 orbit, and this will be the condition of stability of period 3 orbit. When these two conditions are satisfied, then the orbit will actually occur. So on and so forth, you can work out the conditions of existence of all possible orbits. I will come to that in more details in the next class.